So welcome to the 100th Theoretical Physics Colloquium by Professor Andreas Schmitt from the University of Southampton. He received his PhD from Goethe University in Frankfurt in 2004. He had several postdoctoral positions. He spent a year at MIT in 2005. Then he spent 2 years at the Washington University in St. Louis. Then he was a postdoc at Vienna University of Technology between 2007 and 2008, and then became the university assistant at Vienna University of Technology until about 2014. In 2015, he received Ernst Rutherford Fellow at the University of Southampton, where he is an associate professor starting from 2019. He received several awards and honors over the years. He had the Best Physics Dissertation Award in 2005 from Goethe University, and then he had this Rutherford Fellowship in 2015. In 2017, he received Outstanding Referee Award from Physical Review Journals, and that's a very commendable professional service that I would like to highlight. His research interests include matter under extreme conditions, neutron stars, magnetic catalysis and inverse magnetic catalysis, superfluid and superconducting states of matter, transport properties of nuclear and quark phases of matter, holographic methods, and many other topics in nuclear and theoretical physics. And today he will be talking about building a realistic neutron star from holography. And with that, I'll give the microphone to Andreas.
Okay, I'm going to share my screen first. I'm assuming you can see this now, including my cursor.
Everything's fine.
Okay, great. So thank you very much, Igor, for this very kind introduction, for the invitation to give the seminar or colloquium today, especially since the 100th edition. So what I'm planning to do is to talk about a mix of holography and neutron star physics. I'm not going to assume much about holography. I'll try to keep it very light on the theoretical side and mostly talk about the results and how we use holographic methods to build a neutron star and check whether that neutron star fulfills the observations that we have. So this work, I should mention, is based mostly on collaboration with Nicolas Kowensky, who is now a postdoc at Zakaizuki, and Aaron Poole, who was a postdoc here at Southampton, now currently moving to a postdoc in Korea. So the first paper is more of a theoretical operation. I'll talk about this as well. So there will not only be applications to neutron star physics, but also to questions on the phase diagram. And the other two papers, the second one is the main one where we constructed the neutron star. And the third one are proceedings, but we included some new results where we did a more systematic comparison of our results with the observational data. So what I'm going to do is I will start with a little motivation and some basics of this holographic model, which is the so-called Zakaizuki model. As I said, I will keep it very light, try to explain it in terms of pictures, basically. Then I will talk about the more theoretical applications, how to introduce isospin asymmetric baryonic matter, which is not as trivial as you may be used to from ordinary field theoretical models, and also how to couple it to pion condensation and look at some phase diagrams. And finally, I want to talk about the neutron star applications. By the way, this figure here is a little piece of art we made for an internal news release. So that's supposed to represent, on the one hand, the string theory side. You see the brains and the strings here just superimposed with the neutron star. So that's not a calculation. That's just the little image. Okay, as a motivation, let's look at the phase diagram of QCD, which is mostly shown in the plane of temperature and baryon chemical potential. That's this plane here. I've added a third axis here, namely isospin chemical potential. That's obviously relevant for neutron stars, where we have more neutrons than protons. So there's a non-zero isospin asymmetry. And I've tried to highlight a few of the phase transition lines that we know or believe to know, and which we don't know and only have guesses or model calculations. For example, in the T mu plane, most relevant for us is the dense matter part here. So we go from nuclear matter in some way to deconfined quark matter, which is weakly interacting for asymptotically large mu b. But what's in between, we don't really know. One of the candidates I will come back to later is the so-called quakionic phase, which has been pointed out in the large NC limit of QCD. And one of the questions is whether there's some remnant of that phase at the physical NC equals 3 case. The phase transition between deconfined and confined matter, we don't really know. We don't really know where it is. We don't know whether it's a crossover or first order phase transition. That's why I put a question mark here. Obviously, one of the reasons we don't really know the structure here is that we can't do brute force calculations on the lattice. We can do that at 0 baryon chemical potential, even if we switch on an isospin chemical potential. So there's this one line here about pion condensation, which does not have a question mark. So in recent years, people have looked at the lattice on this plane, the T mu I plane. But even there, to the best of my knowledge, if you go to very large mu I, I'm not sure if lattice can make a reliable statement on whether baryonic matter might also appear here, right? So you might also ask, how are these lines connected? If we, for example, look at the mu b, mu I plane, for example, there can be a coexistence of pion condensation and baryons. That's a question that people also ask in the Neutron star context. So whether this propagates in this down in this plane here. And of course, the neutron stars somehow live here. I put them somewhere down in T, but nowadays with gravitational wave signals from mergers, we could even probe into the large temperature direction, say almost up to 100 MeV. But more importantly, neutron stars don't live in the T mu b plane, but somewhere here in the T mu b mu I space. We can already keep in mind that mu I is somewhat smaller than mu b. That's why I put this here. And of course, this raises the question, which phases are covered by neutron stars? So what's the composition of neutron star matter? So this kind of the motivation, bringing together theoretical questions with the astrophysical questions of the project. So the tool I'm going to use, as I already said, is holography. As I said, I'm not assuming that you're all familiar with the details. I guess I'm kind of assuming that you've heard of holography being an equivalence between certain string theories on the one side in some higher dimensions and a field theory on the boundary of this higher dimensional space. And what makes this powerful is that calculations in the gravity approximation on the string side translate to the strongly coupled regime in the field theory side, right? So we can do relatively simple calculations without using full string theory, rather just doing classical gravity in some high dimensional space and translate this to the strong coupling limit of a field theory. So that's a very general equivalence or duality. And now the question is, can we use this for QCD, right? So the best established version of this duality is the so-called ADS-CFT correspondence, where the field theory is conformal, supersymmetric, but we know QCD isn't any of that. So one of the questions is, can holography help to understand QCD? First of all, I should say that you can ask very directly, is there a dual of QCD? And from general principles, you might say, yes, this probably exists. But it's safe to say that currently this is way out of reach. So we can't work with a direct dual of QCD. By the way, on this slide, everything good, everything red is bad. So the problem we have to use some other theory. So we are in the wrong theory, but we are in the strong coupling regime. That's the good thing, which is difficult in QCD. So we have a reliable strong coupling calculation. I already should specify that's usually at infinite coupling. And it has been used, I'm sure most of you have heard about this, in several contexts, for example, heavy ion collisions, where some successful predictions have been made, maybe if only qualitative. I'm thinking of things like eta over S, also of non-equilibrium calculations that can be done and can be brought into context of heavy ion collisions. Again, this is mostly done in the case of the supersymmetric Young-Mills plasma, hoping that this shares some properties with the quark-gluon plasma generated in heavy ion collisions. So what I'm going to do is I'm using a different version of holography, more specifically the so-called Zakaizuki-Sugimoto model, based on already what Witten did very early on. And this is a top-down approach in the sense that there's really a string theory behind this, as opposed to bottom-up, where you just write down some model and you really have no idea at all what the field theory might be. And many people use that as well. There's a string theory behind that. There are only very few parameters. I'll get back to that. But that's already worth emphasizing, because that distinguishes this model from other field theoretical neutron star models, like relativistic mean field models and so on. We do break supersymmetry and conformal symmetry, so we get closer to QCD, and indeed there's some limit in which this model is dual to at least latency QCD. However, that's not the limit in which we can calculate. And originally this has been applied in the vacuum, so for meson spectra, baryon spectra, also glue ball spectra. And what I'm interested in here, and I've used this already in earlier works, I'm interested in the phase structure, not in vacuum physics. And it turns out that for this purpose, this model is also quite useful, at least in a qualitative sense. So here's my little introduction in 3 slides. As I said, I want to introduce the model basically only with pictures without going into any equations. So what I've done here, I've superimposed the T-mu phase diagram with the geometries of the Zakaizuki-Sugimoto model. So for this blue and red plots, the vertical direction is the so-called holographic coordinate. So you can, roughly speaking, think of the field theory living on the boundary here, up here, whereas the higher dimension, or the 5th dimension, if you wish, is here giving this bulk. So that's the extra dimension, plus some more dimensions which are not relevant now, and actually not relevant in the calculation either. So what to take away from this plot is that there are 2 different geometries that are solutions to the Einstein equations. Notice that there are 2 compact directions. This one is easy to explain. That's the finite temperature imaginary time direction that you know from thermal field theory. So changes as I change temperature, right? So this is a 2-dimensional subspace holographic direction, imaginary time. The second compact direction is an extra dimension, and this is compactified giving that scale which breaks supersymmetry and conformal symmetry. So that's a crucial ingredient of the model. And the radius is one of the parameters of the model. So this I will fix later numerically, but this will give me a scale, which is very important to break conformal symmetry. Okay, so these are the 2 compact directions, this one fixed, this one varying with temperature. Then we find 2 different geometries. You see, I don't want to go into details, you see that somehow it rolls. So this is a cigar-shaped geometry, and this is cylindrical. It's a different way around down here. And you compare the free energies of these phases, you see there's a critical temperature above which this one wins, and one can show that this corresponds to the deconfined phase, this to the confined phase. So this is what we expect. We go at a critical temperature from confined to deconfined. Okay. You see this is independent of the chemical potential. So the chemical potential enters in a slightly different way, namely on these branes that I will come to now. So these black lines here is a way to introduce flavor. Maybe you've seen this in other holographic models. These are probe branes. So by assumption, number of flavors much smaller than the number of colors, we just put them into the background geometry, which is given by the colored sketches here. Okay, and they will dynamically either disconnect like this or connect. So why do I have 2 different ones? I can interpret them as left-handed fermions living here and right fermions living here. And that's a very nice geometric realization of chiral symmetry breaking. If they are separated, chiral symmetry is restored. I can do left-handed rotations on that brane, separately from right-handed rotations here, whereas the rotations are coupled or locked in this kind of embedding of these branes. So that means in the pictures I drew here, chiral symmetry is restored if and only if I'm in the deconfined phase, right? So that's what locks these two things together. That's what one finds. And the fact that this is independent of mu is because mu is a boundary value of a gauge field living on the brane. So whatever I do on the brane, by assumption, does not change the background geometry. That's why there's no mu dependence of this line. This is very much like the quenched approximation in QCD, and also gives us a phase diagram that's very much as expected from large NC QCD, which you might have seen before.
Andreas?
Right, so, yeah.
Quick question. I forgot, what exactly is representing confinement, deconfinement in these pictures?
It's not trivial to see from this plot. You can really look at the what happens is if you separate two quarks in the boundary, what happens in the two different geometries, and then you see the confined potential in one case, the deconfined in the other one. So it's not obvious. I'm just telling you here on this level. So
from the picture itself, you cannot immediately tell unless you consider
exactly. I guess you can tell there's some yeah. You would have to know a bit about other holographic models where it's really quite similar, but yeah, it's not so obvious to tell. Okay, so but this is a rather boring phase diagram. Remember all my ambition in the motivational slide that I want to do mu-dependent phase transition lines. So let me show you how this is possible in this model. So what I find is that that a third phase is preferred in a certain region of the phase diagram if I allow the separation of these branes to vary, right? I call this L. So this is another parameter, if you wish, of the model. And what it does is, if it's sufficiently small, as found out in these references a while ago, is that for certain temperatures and chemical potentials, it's preferred to have a deconfined geometry with a chirally broken setup of the quarks, right? Connecting flavor branes. And here we got a mu-dependent chiral phase transition line, right? Now you might say, well, this looks even weirder. That's even further away from actual QCD. But the way I think of this is as follows. Suppose we make this asymptotic separation L even smaller. So relatively speaking, this becomes larger compared to the critical temperature. You can think of this as a decompactified limit, right? Because now, if I'm sitting on these branes, I know very little about the fact that this closes, right? In this sense, it's decompactified. And I can think of this part, if I forget about this confined phase, as a model where I have a mu-dependent chiral symmetry breaking phase transition. Very similar to NJL model.
One question here, slide 5 before. What is KK?
Okay, so I put this condition here. So MKK is the Kaluza-Klein mass. And you can think of this as, well, the inverse of the Kaluza-Klein mass is the radius of this compactified dimension.
Oh, okay, thank you.
Right, so this just means L smaller than a certain fraction of the circumference of this compactified dimension. Yeah. So this MKK is the other parameter of the model. Right, so you can think of this as going into an NJL-like theory in the extreme case of decompactification. And that gives you some non-trivial phase transition lines, also some non-trivial temperature dependence, which you don't have in the confined phase. And NJL, because if you're familiar with NJL, you know that the gluon dynamics are thrown out in NJL. And it's very similar here, right? So the background basically comes from the gluon dynamics. So we're only asking about the flavor dynamics. So this is a nice way of thinking of this if you're familiar with NJL, with the NJL model. Now what I want to do, this was my little introduction. So this is a bit of a bookkeeping slide, maybe for the experts. You don't have to worry about this very much because I'm using both geometries now in the following for different reasons. So this geometry here, the confined one, is easier to calculate. I can put these flavor brains, I can separate them maximally such that they just follow geodesics along that space, and I never have to calculate this embedding dynamically. So that's the simplest calculation I do. The price I have to pay, I will never get some chiral phase transition. The other option I have is I look at this scenario where the calculation is more difficult. What I gain is I get this dynamical chiral phase transition and a non-trivial temperature dependence. So we'll switch a bit back and forth. You don't really have to keep track of that. I'm just telling you here, let's just say the main results for the neutron stars I'm doing in this simple setup, confined geometry, antipodal separation, the simplest thing I can do because the numerics become relatively easy. Okay, so the one main ingredient is missing. I've told you how to construct, or I've shown you sketches of how to construct a gauge theory. I've told you how to add the fermions, namely the quarks, but how do we do baryons? Right? I was promising you neutron stars, so we should have baryonic matter. So here's, again, in very brief words with a few pictures, there is a certain recipe how to add baryons in ADS-CFT in general. You can connect it to your usual particle physics picture of having 3 or more generally NC fermions forming a baryon. There's a geometric construction with this. Never mind if you're not an expert in string theory. What we need to know is that in this particular model, this construction is equivalent to instantons on these D8 brains. And this makes the connection, by the way, to his Kerm model, which some of you may be familiar with. So instantons of the gauge theory on these flavor brains, I haven't said this explicitly yet. So there's a gauge theory living on these flavor brains, which translates to a global symmetry at the boundary. So the chiral symmetry at the boundary in the field theory comes from having gauge fields here, and making non-trivial configurations such as instantons gives me baryon number. That's the point. So I've already schematically shown you an instanton sitting here. It will dynamically pick this place here in the simplest situation. And I call it an instanton because it's just like the instanton you know and love in 4-dimensional field theory, except that the time direction is replaced by the holographic direction u, or some coordinate that goes along this connected flavor brains, right? So strictly speaking, it's not instanton in the sense that it's localized in time, but it's localized in position space and in the holographic direction. That's one difference. Of course, the other difference is that it's an instanton in curved space. Right, so that makes it much more difficult. So this is the difficulty. We have curved space, and of course, this instanton is a single baryon. Right, so when people do baryon spectra, that's what they do. But what I'm interested in is baryonic matter. So I want to do this in curved space and in a many instanton or many baryon system, and that's too difficult. So I need approximations. So let me say in words what the approximations are. That's a bit of a history slide of what people have done. One thing you can do is you can just pretend these instantons have 0 width. They are delta peaks. That makes life much easier. You can write down expressions for baryonic matter where the baryons are point-like. I will use that approximation in the talk on the next slide or so when I tell you how we construct quakionic matter very briefly. Then there are works which really make use of the finite width instanton, starting from the flat space solution and somehow extending or extrapolating this to the curved space. Then the question arises, do you let them interact? Because that's also very difficult, of course. So there are a lot of works using non-interacting instantons. We generalize this to including two-body interactions. I will not talk about this approach in any of the following results. What I will use is what people refer to in this context as a homogeneous ansatz, where we forget about this position space dependence of the instantons. We just write down a very simple ansatz that creates us topological baryon number, but which is not based on the single instanton solution. I will briefly show you in an equation how this looks like. And this is the ansatz I'm going to use for introducing isospin asymmetry on and constructing the neutron stars. So that's the theoretical background of the main results later. Okay, so here's what I want to show. And the approximations, I will very briefly show you quakionic matter because I thought in this audience there are some people interested in that. I will just show you the results, no calculation. Then I will show you how to introduce isospin asymmetry. I want to give you a little flavor of what the calculation consists of. So I have 1 or 2 slides about the formalism, but then just show you the phase diagrams, and I'll try to leave enough time at the end for the main results, if you wish, how to construct the neutron stars from that. Okay, so here's one slide about the quakionic matter. So quakionic matter was suggested by Larry McLaren and Rob Pisarski, basically as a phase of nuclear matter at large NC. That's one way of saying what quakionic matter is. What the name suggests already is that it has some properties of quark matter and some properties of baryonic matter. And what emerged in their analysis already, and what some people have used recently, is a picture of a quark Fermi surface with a layer of baryons in momentum space on top of that. So a layered structure in momentum space. And what we found in our holographic model, actually without searching for it, it somehow dynamically emerged, is something very similar. And we can do this completely consistently. We can compare this phase with other phases, localize this in the phase diagram. And the reason why we call it quakionic is as follows. That's the first picture here. So now you see these, now that's a calculation. Everything I showed you before was just drawn by hand as a sketch. Now that's the embedding of these flavor brains. Again, that's the holographic coordinate. That's the compact direction. The red dots are now point-like, or a set of point-like baryons. They dynamically move up. So we determine this location dynamically, and we add quark matter by strings stretching from the horizon to this point here. So that's why we think there's both quark degrees of freedom and baryonic degrees of freedom. Maybe more convincing even is this plot, where the gauge field, or the temporal component of the gauge field, that's the one that's supposed to go to the baryon chemical potential at the boundary. So that's the baryon chemical potential. It approaches that here, but we nicely see this layered structure here, as if there was a different chemical potential for the quark matter here, up to the point where the baryons sit. Right, so that's what we found dynamically. That's a dynamical solution of the equations of motion that's indeed preferred at some places in the phase diagram. So that's this kind of, I shouldn't call it a mixed phase of baryons and quarks, because it's not no phase separation in position space. It's really this momentum space or energy space, because this holographic direction can be interpreted as an energy scale as well. So this is why we think it's quakionic. These are the phase diagrams we get. Very briefly, let me show you. So that's T mu B, baryon chemical potential in some dimensionless units, never mind the numbers now. And we find that there's, let's look at the transition at small temperatures first. There's a vacuum, the mesonic phase, I should say, a transition to the purely baryonic phase. It's second order, it's not quite realistic. That's because it's point-like, never mind that. And then there's a first order phase transition to the quakionic phase, which we find is chirally symmetric. That's a prediction of this model. That's one of the unsolved questions, even in large NZ-QCD. So in this model, it's a chirally symmetric quakionic phase, and it even never stops to exist at large mu. I should mention that we do not have asymptotic freedom here, so we should not trust large mu or large T predictions from this model for QCD. So let's forget about the large mu region. Still interesting that we never find the pure quark phase here. Not sure what that means. Anyway, there's a quakionic region. This is for 0 pion mass, because that's much simpler in that model. I won't go into details why, but it's harder than in other holographic models to introduce a quark mass or pion mass. We've done this in an effective way here. and we get more complicated phase structures. But roughly speaking, it's the same structure. Notice we can change into a second order phase transition from baryonic to quarkionic, but I don't want to go into details of that phase diagram. I guess that's all I want to say about quarkionic as a little aside. Happy to take questions now or probably later, if you have questions about that.
What's the difference between two quarkionic phases, red and blue?
Yeah, that's a good point. That goes into the details already. It's a dotted line here. We think that some kind of maybe artifact or large NC effect. It's a slight difference in geometries in the holographic model, but we go, let's say, more or less continuously from one to the other. We haven't really understood a clear physical difference. It's a good question for the future, yeah. Okay.
There's one question here. The slide before here. Here. The color is number 3. The color is 3, like both baryons.
Well, our model is valid, strictly speaking, for large NC.
Okay.
But we have done all kinds of tricks, like remember this, right? So this looking at the model in this limit, which we do here, creates this phase diagram, which is different from large NC. So the philosophy is, in holography, going away from the large NC limit, strictly speaking, is very hard. So what we do is this trick where we get some features of large NC and use this, if you wish, as a phenomenological model for hopefully finite NC QCD. That's the philosophy here, right? If we were strictly at large NC or infinite NC, there would not be such transition lines here anyway. All right? But otherwise, there's no point in the calculation where we have to choose a value for NC. That's all hidden in this dimensionless units here. If I go to physical units later in the Newton-star context, I just set NC to 3 by hand, thinking of an extrapolation from large NC.
Andreas, there is a question in the chat asking what are the units for T and mu. So how do
I said this for now. For now it's dimensionless units. It doesn't make much sense to talk about this at this point of the talk. I have to choose a value for MKK basically, and for the 't Hooft coupling and for NC to translate this into physical units. I'll get back to this in more detail later. So let me maybe keep this brief here, because this is really only about the qualitative picture at that point. Okay, before I get to the results for the neutron stars, let me say very few words about the formalism, so you get a flavor of what we're actually doing. So what we do is we look at the brain, the action, gauge field action on these D8 brains. It has a so-called dBi part, the red one. If you've never seen this before, think of expanding this for small alpha prime, the string tension. So you get F squared terms, which would be Young-Mills, right? So that's the dBi part. Then there's a transaminds part, which is very important because this is the topological baryon number. This is some FF dual term, which couples to the abelian part of the gauge field, which you can think of the mu B, the mu baryon. I should say this stands for a space-time. Z is now a parametrization of these connected branes. So I'm switching between U and Z. So think of this as the holographic coordinate. So we work with 2 flavors, which gives us an abelian and a non-abelian part. So that's SU2 part, that's the U1 part of the gauge group. I put the hat on the abelian part. So this A0, for example, is the abelian part. These Fs without hat are the non-abelian ones. I introduced the chemical potential at the boundary as a boundary condition for the abelian part of the temporal component. You know this from ordinary field theory, right? The chemical potential is basically the temporal part of a gauge field. I create baryon number, as I said, with this transaminds term here. Think of this as a mu times n term in thermodynamics. And this is where for example, the instanton configuration, for example, it would give me a finite baryon number. I introduce an isospin chemical potential in the non-abelian part of the temporal components, right? So the think of the third Pauli matrix where I put my mu I. There's a little subtlety here. I can choose different kinds of boundary condition depending on whether I include pion condensation or not. It's interesting that this can be translated into the boundary conditions. That's not obvious. Let's just let me just mention that as a little technical point. So we can introduce pion condensation in addition or coexisting with baryons if we just look for different boundary conditions. For most of the following, I set m pi to 0. We are just looking at finite pion masses currently. This is the homogeneous ansatz for the baryons I already mentioned. What we basically do is we take our gauge field components, the non-abelian ones, and just put this single function h here as a function of the holographic coordinate. This requires a discontinuity, so that's includes some approximations, but that's the simplest way how you can introduce baryon number. And it's in some way equivalent, not equivalent, but in spirit the same as the instanton approach. It's supposed to be valid at large densities because it's some kind of averaging of a position space. So when the instantons overlap very strongly, we believe that's a good approximation. Then to mention technically what we are doing, we set up the equations of motion, the classical ones, right? As I said at the beginning, that's the CFT correspondence. We now only have to solve the classical equations of motion for the gauge fields. And if we also look at the embedding function that's coupled to it, and we can do this for any mu b, mu I t. So remember my motivation at the beginning. Now in principle, I can determine the preferred phase in each point of the phase diagram, not in QCD, in my phenomenological, semi-phenomenological string theory inspired model. But anyway, this I can do now consistently. And I compare the free energy, I plug it back, plug the solutions back into my action. That gives the free energy, I compare them and determine the ground state at each point. And I can check for the vacuum, for pion condensation, for baryonic matter, and for the coexistence of pions and baryons. I will now stick to mostly to the confined geometry, so I will not look at chirally symmetric matter in almost all of the following results. Okay, so here are a few results. That's a bit of a warm-up plots for the neutron stars. So what I can do is, for example, let's look at this upper plot here. I can plot the baryon density as a function of baryon chemical potential. Let's look at this curve here. That's small mu I. Let's pretend that's 0 mu I. So what I find is some first order phase transition, right? I move along in the vacuum or in the pion condensed phase, but you can think of this as a vacuum if you wish. And then there's an onset, a first order onset, as we know in symmetric nuclear matter to the baryon phase. And this changes if I change mu I and we get these solutions. That's probably a bit difficult to understand what it really physically means. So let me translate this right away into the phase diagram. I will now stay at 0 temperature. So that's mu b, mu I. What I just explained is going along this direction. I have this pion condensed phase or the baryonic vacuum, first order transition with baryons. And interestingly, we find this coexistence phase is preferred in a large region of the phase diagram, basically everywhere except for this except for this quarter circle like region here. I've included a blue line here. That's interesting for later for neutron stars. That's better equilibrated neutral matter, which we believe is present in neutron stars. And here you see in these units, again, I will only come later to the physical units, but in these dimensionless units, you see that mu I is relatively small compared to mu B in neutron stars. That's what we can take away from this already. Now, one obvious artifact is that in the case of vanishing pion mass, there shouldn't be or let's say it like this, in the real world, there shouldn't be a pion condensed phase at arbitrarily small mu I, because that should only start if mu I is larger than the pion mass. right? So in that sense, this is an artifact. And that's exactly what we are working on right now. So let me show this as a preliminary result. I won't go into any of these features, which are quite interesting. We are still trying to understand and interpret this. But now, if there's a physical pion mass, obviously, let's stay down here. We go from the vacuum to the pion condensed phase if we cross the pion mass. And one of the predictions we have is in the baryonic matter, we go from pure baryonic matter to the coexistence phase across this second order onset. So this can be interpreted as an effective pion mass in the baryonic medium. So that's a prediction of the model that the pions get heavier in baryonic medium. I think that's what other models predict as well, because people think or tend to think that there's no pion condensation in neutron stars, right? If I put this blue line now here, we haven't actually done it, but I think it would not cross this dashed line. I will actually have to check this. But that's one of the predictions we get now in the presence of the pion mass. There are other features which we think is now more realistic, but let me skip this because I want to have enough time for the neutron stars. I will also skip the finite temperature bits, which we did. Let me really save enough time, last 15, 20 minutes for, 15, I should say, for the neutron stars. Okay, so this was the preparation. I should mention that among the holographic models, we were the first ones to really introduce isospin asymmetric nuclear matter. There are other holographic works, I will mention them later, or where you can find them, which just pretend it's all symmetric nuclear matter or symmetric quark matter. And then they construct neutron stars as well. So the advantage here is that we have isospin asymmetry. So what we do now is we are, in a sense, ambitious and say, can we construct the entire neutron star from our holographic model? That's also different from other approaches where often the core, the densest part, is constructed from holography, and the crust or the low density regions are taken from traditional models. And you might argue it's sensible to do that because at low density, we understand what's going on. Why would we need holography, right? You could ask that question. And that's true. But what we gain, of course, is that we have a fully consistent picture of the whole star. In particular, we can determine the crust-core transition, where it happens, at what density it happens, fully consistently in that model, right? Whereas in other cases, you just have to assume a certain crust-core transition. So that's what the philosophy is. Now, how do we do this? So we take the asymmetric nuclear matter that I constructed before, that I explained before. We add leptons, so we can easily do this. Just that has nothing to do with holography. We just take a non-interacting electron and muon gas, add it to the free energy that we get from holography, and make the nuclear matter neutral. Right? So we now live only along this blue line here in neutron stars. That's how we do the core. That's easy. The crust, if you're not familiar with neutron stars, the crust is supposed to be very similar to a solid state on Earth, at least qualitatively. So we have a lattice of ions, if you wish, so nearly symmetric nuclear matter in these clusters here, and a lepton gas surrounding it, right? And what we do is we use holography for these bubbles and construct this mixed phase dynamically by assuming a sharp interface and assuming a surface tension. That would be our one additional parameter that we introduce. We use a surface tension at this boundary, but otherwise then dynamically determine the size of these bubbles and where they are preferred energetically. Okay. One thing I should mention as a little caveat, we don't, or I'm not sure if it's a caveat, but in the holographic picture, we don't really see the degrees of freedoms of neutron and protons. So we have to translate the isospin components into neutron and proton component because we want to assign charges to them, right? Neutral and charge +1 for the proton. I come back to this later because that does introduce one artifact. So I said this, we construct the locally neutral matter for the core and the globally neutral matter in the crust. And we use certain, let's say we use certain approximation, a Wigner side cell approximation for this, and step-like interfaces, as I said, for this mixed phase. But nevertheless, once we've done this, it's all purely dynamical, how large the crust is, how big the clusters are as a function of density as I'm going along the profile of the star and so on. Okay, so what do we find? So here's, now I'm switching to physical units. I'll say in a second how I fix the parameters, but let's say I fixed them in a certain way. And here I'm plotting the free energy. I'm plotting them as a difference to the mixed phase where I neglect surface tension Coulomb effect. That sounds complicated. Let's just say it's a simple way, or the only easy way to plot them and see these differences, right? So what I want to check here is which is the lowest free energy for a given neutron chemical potential. So you can think of moving inside the star as I move up in mu n. And what I find is the vacuum is not trivial because I've subtracted this phase, right? That's why I mentioned this. So this is the vacuum. It's preferred up to a certain point. So here we are outside the star. Then the mixed phase takes over. That's the crust. Sigma equals 1 means I had to choose a certain value for the surface tension, 1 MeV per Fermi square. And then there's another transition to locally neutral nuclear matter. So this is the crust core transition here. As it happens, if I scale it in mu n, this looks much bigger than that, but translated into thickness, this will be smaller in the Newton star. So that's our construction. As I said, everything purely dynamical. So this dashed line is now predicted by the model. Here I'm plotting the proton fraction as a function of baryon number. Again, going from left to right is going inside the star. Qualitatively, what I find is very nice, what we expect. So I start nearly symmetric in the outer layers of the star, in the crust. So the red line is for the crust. Then I jump here, because I'm plotting it as a function of NB, there's a jump in density. So I jump from here to here in the crust core transition. So I go down and then up again. Also, that is in agreement with what many models predict. The star here is the location of the heaviest star we find. So for some heavy stars, we even go down for extremely dense matter again. You see, this is a non-monotonic behavior here. So that's all nice and expected. What is probably a caveat is these numbers are very high. You see this never goes below 45% protons, whereas in nuclear matter models, we are more like in the 10% regime, and this goes up. This can go up to 40% or something in the core, but we never go down. We understand why this happens. It's not easy to fix, but that's one artifact we have. Large proton fraction. Another way of saying this is for the nuclear physicists in the audience, it's an extremely large symmetry energy. So it costs a lot of energy to go away from the symmetric nuclear matter. But we have to live with this for now. Okay, so now let me talk about how I fix the parameters. I do have the TOF coupling and the strictly speaking, the calculation is valid at large TOF coupling only, but I'm extrapolating down. That's the usual philosophy. And that's why I said I only have two parameters. I'm getting the message my internet connection is unstable. I hope you can still hear me fine.
There was a small glitch in the sound when you were talking about the parameters.
Okay.
So when I repeat it, it would be actually probably okay.
Okay, the message is also gone now. I hope it works now. So I mentioned before, I only have two parameters. Again, that's remarkable if you compare it to other nuclear matter models. And these parameters are the TOF coupling and the Kaluza-Klein mass. And because of our construction of the crust, we have another parameter. That's the surface tension between our holographic nuclear matter and the vacuum. Okay, so how do I fix them? So what people have to, you can look at the vacuum. Let's say we fit them to the pi decay constant, and the rho meson mass gives two values for lambda and MPK. Then you can say, let's look at the string tension of QCD, for which there are lattice results, and you get slightly different values. Then let's say, let's fix them to saturation density that's closer to what we actually want, right? Nuclear matter, and the binding energy of nuclear matter, and you get different values again. So strictly speaking, if I want to match everything, I should stop here. Not possible. But that would be asking for too much, right? I'm not in QCD. I'm in a model, and I only have 2 parameters, so I should be more modest. I should rather say they're all in the same ballpark, right? Lambda of the order of 10, MKK of the order of 1 GeV. So that's the area where I should be looking at, right? And that's what I'm going to do for the neutron stars. So now I translate my equation of state, right? All the thermodynamics I explained to you from the holographic model translates into an equation of state. Obviously, this is coupled to gravity by the Tolman-Oppenheimer-Volkoff equations, and I get mass radius curves for the resulting stars. So these are these curves, and for each of these curves, I've chosen a pair of lambda MKK. So these are the 2 values. Let's not look at the exact details. The take-home message is that the maximum mass is around 2 solar masses. That's what we need. So the gray band, I put a gray band for all values larger than 2.1, because that's the heaviest star we currently know. And there are some curves that fulfill it, some that don't, if I stay within this region. I'll get to the radius as well, but we'll see the radius also fulfills astrophysical constraints. I can also look at the tidal deformability. That's an observable that we can extract from the neutron star merger that we observed by gravitational waves. Again, the band is the observations, just using a sharp cutoff for some confidence interval given in the observational paper. And interestingly, all 4 points, so this is for a 1.4 solar mass star. So for each case, I have to look at a 1.4 solar mass star. All these points lie in the band, very nice. Also notice that these are 4 curves, and it happens that they are almost on top of each other. This has also been seen in other works where there's some universality with respect to the equation of state was pointed out. I should say this is compactness, so radius over mass of the star. So as a function of compactness, you find this kind of universality relation, and we reproduce this. And in particular, we fulfill the constraint of the tidal deformability from the neutron star merger. This plot I want to spend a minute explaining. I just copied the one from, but let me explain this plot here. So this is now the equation of state. So pressure versus energy density, again, physical units, for the values that I've chosen on the previous slide. So for 4 different cases, 4 different colors. So what's the gray band? The gray band is taken from this paper. What they have done is they have connected chiral effective theory models for low density nuclear matter. So we believe that's solid ground, first principles in a sense. Right, that's this little band here, the gray band here, which they stop at some point. And perturbative QCD at very high densities. So we also believe that's first principle, which they stop at some point coming from above. And then using the constraints from astrophysics plus consistency constraints from thermodynamics, they claim all equations of state of QCD, well, I should say the equation of state of QCD has to lie within that sausage-like band here. So what we can check now.
One question here.
Yeah.
Only perturbative QCD. Use it here.
Perturbative QCD were used for ultra-high densities and effective theories for nuclear matter based on the symmetries of QCD and having a controlled expansion used down here. Okay, so to connect it to our model, in our model, one could say it's not asymptotically free. It could happen that our heavy stars probe some region where we are outside that band, right? That's a question we were asking. And we find, so these dots here are the heaviest stars. These are the 1.4 solar mass stars. So we find they're inside the band, which is very nice, right? So that means we can use our model up to a certain point, and we say we don't trust it anymore, but we can consistently still connect it with perturbative QCD if we want to. Another feature to point out is that we also deviate from this low density band here. Maybe not too surprising because we use this simple construction of the crust. But I don't have too much more to say about this. It's maybe would still be nice to understand this more deeply, but since we use this simple construction of the crust, that's probably not too surprising. Okay, on the last slide, before I get to the conclusions, I want to exploit the fact a bit that I only have two parameters only, right? I emphasized this several times, but because of that, we can do things that usually people in the Newton star context can't do. We can just scan the whole parameter space. It's not that hard. It's just two parameters, right? So what I did here is we looked at all values of the Toft coupling well in a certain range between 1 and 100. And what I've done, if I've determined the Kaluza-Klein mass for each lambda such that I produce that my heaviest star is 2.1 solar masses, that's the blue line, or such that it is 2.5 solar masses, that's the red line. It's a band, not a line, because I also vary the surface tension, right? That's the third parameter. That's why it's a band. And that gives us an idea of how much our results depend on the surface tension parameter. But the interesting thing here is, so I'm plotting the tidal deformability of the 1.4 solar mass star. That's for which we have the observations. That's the gray band. One interesting thing is we have, independent of everything, all parameters, no matter what our parameters are, we have a lower bound of this value, right? Because this blue band curves up. So no matter what our parameters are, there's a lower bound. Because if, of course, you could say I can also create different maximal masses, but I can't go below 2.1. I know this from observations. And if I go higher, I go up. Right? So there's a very general lower bound that we can extract. We also see that if our equation of state produces 2.5 solar masses, we are already slightly in conflict with this. Right? So this gives us also, even though naively without looking at constraints, we can go to very high masses, but looking at the constraints, we will be constrained to something like 2.4, 2.5 solar masses by combining the holographic model with the constraints. I put the radius also here. I guess let's just say the blue band is also in agreement with the observations. If you want to look at a more systematic evaluation of this, where we also really extracted some numbers, check out these proceedings here, where we included all the known NICER results. So NICER is the detector with which the radius has been inferred. Finally, let me get to the other holographic approaches, which I mentioned in words. I decided not to cite the single papers because we have two very nice reviews by now written very recently. So they list all the holographic approaches to Newton star. So have a look there if you want to look at other holography models that look at Newton stars. As I said, that all of them, they combine this with traditional approaches. So we were the first ones to do the whole Newton star with holography. We are approaching 60 minutes, so I should stop here. So the take-home messages are that the holographic Sakai-Sugimoto model gives a QCD-like theory where we have all the necessary ingredients to do phase diagrams. They may or may not be realistic in QCD. We hope they capture some features of it, but we have a current phase transition. We do know how to include baryons, also pion condensation. Since recently, we know how to do isospin symmetric baryon matter. That opens the window to Newton stars, also to the phase structure in the mu-I direction, which is also interesting to compare to lattice if we set mu-B to 0. And there are obviously certain questions that are raised that one can do. Maybe the most difficult one is to improve the holographic description of baryons. I mentioned a few artifacts from large NC. The crust itself can be improved. I've not looked at an inner crust where there's a mixture between a pure neutron phase and a nearly symmetric nuclear matter phase. We've ignored this so far, but people find this in other construction of Newton stars. We are recently looking into including a pion mass. We basically know how to include a magnetic field. We've done this in simpler situations. The surface tension, which was a parameter, we could think about calculating this dynamically. We have not included strangeness. Also, this in principle should be possible. We could ask for holographic hyperons. And in this last part where I was talking about Newton stars, notice I've never talked about a quark-hadron phase transition in the star. It was purely hadronic. So we could also ask about quark hadron or quakionic hadron phase transitions. The problem with this model is that they tend to be at very high densities. That may also be an artifact, but in other holographic models, that is certainly possible. Okay, thank you very much for your attention. I'm happy to answer questions now.
Thank you. Thank you for a nice presentation. So now let's have some time for questions. If you have a question, please raise the hand. And we will go in the order of raised hands. Giorgio Torriera, please go ahead.
Yeah, thanks for a great talk.
Hi, Giorgio. Yeah.
Just as a hi there. Hi there. Since you mentioned, I mean, quarkyonic matter, and of course you said that this finite high density stuff is particularly sort of bad at large, being described at large NC. No, not holography, large NC in general. I mean, you know, you have crystals and you have huge binding energy and stuff like that. So there might be something interesting happening as NCs vary. I mean, there is good physical arguments about this.
Well, go ahead.
Is there a hope? I mean, just even from a qualitative point of view, to include something like this? And I mean, I know that for you have to quantize gravity to go down in NC, which is a much more complicated thing. But yeah,
yes. I mean, as I mentioned, taking this model completely seriously, introducing finite NC corrections even, let alone going to small NC within that model, that's pretty much, well, let's say that's very difficult. There are some attempts also in other models. But of course, what we are trying, of course, I'm aware that large NC can make a big difference, especially at high densities, right? So that's why in this approach, in a way, we take a quite phenomenological path, right? We do this averaging over the instantons. So in my view, this is more on the level of a phenomenological model where we have some honest strong coupling calculation, but go away from QCD and from the strict large NC or extrapolated large NC result. That's my modest approach here. And it seems we can get at least some non-trivial phase structure, which then can later be used as input or as guesses for more elaborate approaches. That's my point of view, I guess.
Okay,
thanks.
Let's move on to the next question. Rob Lizarski, please.
Hi, Andreas. Very nice talk.
Hi, Rob.
I just wanted to make a comment to Giorgio's question that there are simulations on the lattice for two colors, which is like isospin chemical potential. And they find a region where the Polyakov loop is small up until very high chemical potentials. So that's evidence that it's not, quarkionic phase is not special to large NC. Of course, you know, then baryons are bosons, and there's a large region where it's different, but at least in that sense. I just wanted to ask you, so what happens if people discover a 2.7 solar mass neutron star?
In this particular model?
In general, right? They keep getting heavier and heavier, right? There's now a 2.3 candidate, I believe.
I think in this model, at least in this approach, we predict, this wouldn't work. We can't get that high. Given this plot I'm showing you here, right? We would be in conflict with other observables. More generally speaking, the same is true for many other models. So many other models would be in trouble if we did observe that. Yeah.
Yeah. No, I'm being deliberately provocative. Thanks. Very nice.
Okay, thank you. Any other questions from the audience? I actually have.
Oh, okay.
Igaros, did you want to ask? Go ahead.
Yeah. Okay. Actually, again, nice talk here. Two questions here. Look at the slide summary. Shoot here. The slide one here. One question. Oh yeah, summary here. It talks about no strange stage baryons here.
That was
the-
the next page, outlook.
The outlook,
Right,
yeah.
He just mentioned his slide here, but not work on it, right?
But not what?
Did you work on it?
Strange baryons.
Did I work on it? No.
No. In the future, you had to work on that.
Yeah, no, it's on the list, absolutely, because remember that the flavor symmetry, so
Exactly,
the global
exactly.
symmetry in the field theory translates to the gauge theory in the bulk, right? I would have to extend the gauge theory to an SU3 gauge theory, so conceptually it's clear what to do.
Yeah.
And
But it's not easy, right? It's not easy. Have to work a lot here.
I'm not sure because of all the approximations I've already done. Maybe it's difficult, but it's certainly on the list. It's some of the things. I think the first point is harder on this slide.
Oh, again, one question last from here to take. The speaker is German?
Yes,
Speaker is German?
Yes.
yes.
I know that. Okay, thank you.
Okay, next question. Graziano Mileta, go ahead.
Okay, thank you for your talk. I did not understand, perhaps it escaped me, what are the experimental data that confirm the holographic model? And then the surface tension depends on the forces in the phases of matter. What are the tension forces that could produce a surface tension to separate the phases? Do you
So what I'm
understand?
doing here, experiment, I'm using the model to make predictions for mass of a neutron star, radius of a neutron star, tidal deformability of a neutron star, and then I'm checking whether that's in agreement with the experimental data.
Mm-hmm.
Right? Obviously, I can't say that the data confirms the holographic model. That's the wrong way to say it. I'm just checking whether I can reproduce that data. Right? So the surface tension, I'm not sure I completely understand the question. So for
I
the
believe the
surface
question was about the origin. What's the origin of the surface
The
tension?
origin of the force, the tension force.
So I'm not sure if I think of it in terms of forces, but what I mean is, suppose you have the lepton. Think of like a wall or domain wall, where on one side you have the holographic nuclear matter, on the other side you have the lepton gas. In the case where they have the same free energy, right? So you can interpolate from one to the other. So then in between them, you would have to go over a maximum in the free energy, and that costs energy. That's what the surface tension is. That's what it is across these interfaces. So I could calculate that in principle by constructing this interface microscopically.
Strictly speaking, I believe the origin is electromagnetic and strong forces.
Electromagnetic, electrostatic, no, electromagnetic.
Well, in this case, yes, there would also be electromagnetism in it, yes. If I'm in the simple situation I was describing, you can also think of it first without electromagnetism. Just look at, I don't know, symmetric nuclear matter and the vacuum, and then it's the strong forces. Yeah, okay, maybe the short answer is strong forces and electromagnetism, if that was the question.
Okay.
Okay. Thank you.
Okay, let's move on. Other questions from the audience? I had a question, very simple question of my own. When you were talking about the fixed geometry and then putting some probe brains and all of that, essentially it means that it's like the phases that are dominated by the gluons. So in the region of baryonic matter, somehow that seems to be contradictory to think that baryonic matter is dominated by the gluons. So the geometry that is due to the gluons should definitely be affected by the fact that we have baryonic matter. Isn't that right?
Well, it doesn't in the probe brain approximation, large NC.
No, I understand that in that model, but I mean, forget it for a second about the model. We are just considering baryonic matter at a large baryon density. Somehow, intuitively, you would think that this phase is dominated by the baryons, not the gluons. Wouldn't that make sense?
Yeah, but that's what it is. I mean, otherwise I wouldn't get, I mean, the phase structure doesn't know about the gluons, right? I guess the way of saying
but
this
you
is,
don't modify the geometry as a result of the fact that it's dominated by the baryons. You still have the embedded geometry essentially fixed.
Okay, I understand. Another way of saying this is if I increase mu, then of course the pro-brane approximation gets worse and worse. That's
Right.
one way to answer, and that's correct, of course. Yes, I'm just keeping the pro-brane approximation and not worrying about this even at large mu. Yes.
Okay, so then the follow-up is this. How do you adjust the geometry to make it more self-consistent?
Well, that's very hard. Well, here obviously I don't, but you would have to, would have to self-consistently recalculate the red and blue geometry in my sketches.
I see.
Conceptually, that's what you would have to do. But that's very hard. Yeah.
I see. Okay. Any other questions?
I have a question. Thank you very much for a good talk. I'd like to know how your model predicts, if at all, have you given consideration to things like tidal deformities and neutron star mergers with your model?
Well, the tidal deformability I did calculate, right?
Yeah,
for example,
just how it, does it? We only had that neutron star merger, but how does your model? Does it even have predictions for tidal deformities during these mergers? Because you have a nice model with the crust and the core. Well,
I don't know what else to say. Here it is.
It's consistent with the mergers.
I'm still suspecting I don't understand the question because this lambda.
All right, it's consistent with the mergers and the gravitational wave observations.
Well, the gravitational wave observation is the gray band.
Okay.
And the model is the red and blue, assuming two different maximum masses that I can get with the model.
Okay, now I understand that. Okay, perhaps I'm not phrasing my question right. Thank you.
Okay.
Okay, other questions? Well, I do have another one, which was very early on. You mentioned about the magnetic field, that it's possible to include. This is, I didn't remember, this was in the Outlook. So is there any sort of expectations how a strong magnetic field will affect those neutron stars in this model?
Well, I'm not sure if that's the most relevant question because we kind of know that these magnetic fields have to be ridiculously large to affect QCD matter, right? The equation of state. I'm not sure I want to spend too much effort in calculating this, and that would be the same in this model, right? So when I say include magnetic field, I guess I'm thinking more about phase diagram questions, more theoretical ones. Mm-hmm. Obviously, yes, I do have a crust, and in the crust, magnetic field questions are non-trivial, right, for the electrons, but then I wouldn't use the holographic model. I would use more traditional.
Then I simply misunderstood what was the Outlook. I see now, it's fine.
Yeah, it's more for the theoretical part. I don't think I ever mentioned magnetic field before. Maybe it was on the slides only, but yeah.
Right, it's okay. Did I see another hand when I was asking a question? I thought there was something, but...
I was just wondering, did I miss the plot of the speed of sound? I apologize if you showed.
No, there was that's the first talk you have heard in half a year where there's no plot of the speed of sound.
So could I ask how it behaves versus?
Actually, we do have it in our paper. I have to remember. It does have a maximum even without the quakionic phase. That's one thing that's interesting for you probably. So in the nuclear matter phase, it has a maximum, not very pronounced.
Maybe you could go back to the pressure versus energy density. I believe you had that plot.
Yeah, but it's hard to really look at.
No, it's actually, you could see that there is a slope in this middle, which is much higher than anywhere else. So there is a peak. There has to be.
Yeah, maybe. So yeah, so there is a peak. It goes above 1/3. I guess otherwise we wouldn't get the realistic neutron stars. It does not go asymptotically to 1/3, right? It's not asymptotically free. So in that model, it would asymptote to some value above 1/3. So that's unphysical. But of course, the neutron stars live somewhere at lower densities where it's somewhere above 1/3. I forgot whether the peak is included in the neutron star densities or not.
I see, but in other words, you're saying in other models, they need a sharp peak to match onto the perturbative limit at high densities. And you're saying if you forget about that, you're just staying above the conformal limit and you can still get very heavy neutron stars.
I don't think that I need the peak in the sense that I have to go down.
Right. I see. Okay, no, that's interesting.
Yeah, that's indeed a very good point. Yeah, I should also compare to what we heard last week on the conference. But of course, the reason why I say I can still connect to perturbative QCD, it's that plot here, right? I haven't looked at the speed of sound plot, but in this plot, I can see I can connect to perturbative QCD.
Okay.
Yeah. Thanks.
Okay. One last question that I had still here. You mentioned about very large symmetry energy. Is there any way of reducing it in this model?
Yeah,
it was unrealistically large, I believe.
Yes, the problem in this model is that if you look at the isospin direction, the spectrum is continuous in the version that we use now. I guess that's the large NC effect, right? So there's no neutron proton, but it's a continuous spectrum. That means symmetric nuclear matter is made of mostly isospin 0 baryons. And if you want to now make isospin asymmetric matter, you have to create heavier baryons, not just reshuffle the neutrons and the protons, but make heavier baryons. That's why it's on the order of the mass, which is different in QCD, right? So we have 30 MeV symmetry energy, I think, but we get factor 10 more or something for the reason I explained.
I see.
Right. So what we would need is this quantized spectrum, in the best case, neutrons and protons. And in that model, people have done this for single baryons by quantizing the bulk calculation, right, in the higher dimensional space. But combining this with our many-body approach, that looks very scary to me. That would somehow be the way, but it's certainly difficult. But it's maybe worth trying to make it more realistic. Maybe the question then is, why does it work so well, even though we have this large symmetry energy? Maybe that's one question one can ask.
So, and if you ask, what's the answer, if you happen to know it?
I don't know. Maybe I don't know if we compensate for that with other artifacts that I'm not aware of, or whether it just doesn't matter much, or if any vaguely reasonable approach gives good results. Maybe that's what it means. I don't know.
Right. Okay, fair enough. I don't see any other questions, so I want to use this opportunity and thank Andreas for a very nice presentation.